Hey, welcome back to chemistry, and today what we're going to do is we're going to continue on with some balancing equations. And so now the equations are a little bit more difficult, so we're going to try some of those. So I have here some recommendations on how to balance equations. So the first recommendation is to make sure you make a little chart and where you're listing for each element the number of atoms of that element in the reactants and the product side of the equation. That usually can be very helpful. The second point is if you seem to have an element that's by itself and where the element is not involved in several compounds, it's just alone as an element, a single atom or a diatomic element, then you might want to use that one last. Okay. The next bit of advice I might give is a lot of times you'll see oxygens and hydrogens split up between multiple compounds on either the reactant side or the product side of the equation. If that's the case, then I would recommend just waiting for those until either the last to balance or the next to last to balance. And so they would be next to last to balance if you have a lone element on either the reactant or the product side. And one thing that can be very helpful is if you see polyatomic ions in your equation, you can balance whole polyatomic ions, but make sure that the atoms of the polyatomic ion are not distributed in other compounds, and then you can't really easily do that, but that's something you can keep in mind. Okay, so let's go ahead and try a few equations here. So I'm going to put up the first equation. Okay, so let's go ahead and try to balance this equation. So first I noticed that there really are no lone elements on either the reactant side or the product side of the equation, so we can't really get help any there. However, one thing I sort of noticed immediately is that there are polyatomic ions, and so what I want to sort of check is to make sure that the polyatomic ions are sort of by themselves between the reactants and the products. And so for example, I'll draw a line up here above NH4, and then I see another NH4 here. And so these look like these can be balanced as whole ions. Also, I see nitrate here. We have two of them, and we have nitrate here. And so these are balanced as whole ions. Now, one thing that might get us into a little trouble is, let's say we had nitrate here on the left side, and maybe we saw it on the right side, but we saw additional compounds with nitrogen and oxygen. Then it might be a little tricky to balance the nitrate ions as whole ions, but we didn't really see that. So I think we can go ahead and try to balance this equation out. So I'm going to make my little chart. And then what I'm going to do is I'm going to, in addition to elements I want to balance lead, iodine, but let's balance whole ions like this, NH4 for ammonium and NO3 minus for nitrate. Okay, so let's go ahead and balance the polyatomic ions first and see what that happens with that. But before I do, let's count ions. So we have one ammonium here on the left, on the reactant side, one on the right. With nitrate, we have two on the left, one on the right. With iodine, we have one on the left, two on the right. And with lead, we have one on the left, one on the right. So it looks like, so far, everything is balanced except for the iodines and the nitrates. So let's go ahead and balance the nitrates first. So we have two nitrates there. So how do we easily get two more nitrates? Now, don't do what I'm about to do. So one thing you may be tempted to do is put in parentheses here and then a little 2 subscript. You cannot do that because then you change the formula of the equation, and you cannot do that when balancing equations. You can only really work with coefficients. So here we've had two nitrates on the left side of the equation, we have one on the right. You can put a 2 here, that you can definitely do. And so now the nitrates appear to be balanced. Now, one thing that happened in this process is it looks like we threw the ammonium ions out of balance. So now we have 2 on the right 1 on the left. And so how can I deal with that? Let me just go ahead and put a 2 here and see if that balances the ammoniums and see what happens to other things. Okay, so one other thing we needed to balance was iodine. So we have 2 iodines on the left and 2 on the right, so that is balanced. The leads are okay with 1 atom of each on either side of the equation. So it looks to me that this equation is balanced. So let's go to the next one. Okay, so this is number 8. So C5H12 plus O2 gives you CO2 and water. Okay, so let me make a chart here. We don't have any polyatomic ions, so I think I can go ahead and make a chart for the elements that are there. So, carbon, oxygen. Okay, so do we have any elements that sort of stand alone on one side of the equation? Yes, we do, and that would be oxygen. So we may want to consider balancing that last. Now, another comment I can sort of make about this equation, this is a particular kind of reaction, and there's a certain way or a certain order which is helpful to know for this particular kind of reaction. The reaction is called a combustion reaction. A combustion reaction is when you have some kind of hydrocarbon. We know that this first molecule here is a hydrocarbon because it only has carbon or hydrogen in it. It could be a carbohydrate as well if it had oxygen in it, but it's not. So this is just a hydrocarbon. When you have a hydrocarbon reacting with oxygen, producing carbon dioxide and water as products, that is combustion reaction. And so my recommendation is if you see this on the test, you leave oxygen for last. And then what you do is you balance the carbons first, then the hydrogens, and then last oxygens. And usually that goes pretty well. Although some combustion reactions, as you'll see, it can be very difficult to balance. So let's go ahead and try this one. So first, let me just note how many atoms I have of each element here. Okay, so you can see all the atoms at this point are out of balance. So let's balance the carbons first. So I will put a 5 here. And so the carbons are balanced. Okay, so now I want to balance hydrogens next. So we have 12 on the left and we have 2 on the right. So it looks like maybe if I put a coefficient of 6 here, then we will have a total of 12 on the right. And now the hydrogens are balanced. Excuse me, we're now up to 12. Okay, so what we have to deal with last is the oxygen. So let's count the oxygens on the right side of the equation. So there are 10 oxygens here in carbon dioxide total. There are 6 oxygens here in water total. So it's 10 plus 6. We have 16 oxygens. So here on the left side of the equation, we have molecules of oxygen with 2 atoms apiece. So if we have 16 on the right side, what do we add as a coefficient to balance? We add an 8 here, because now 8 times 2 is 16. So now we're up to 16 on either side for the oxygens, and so this should be balanced. So let's move on. Okay. So this is another combustion reaction because we have a hydrocarbon reacting with oxygen to produce carbon dioxide and water. So we need to make our little chart again, which could be helpful. Okay, so let's count atoms to see where we're at right now. Okay, so that looks fine. Okay, so as I said earlier, I strongly suggest you balance carbons first, then hydrogens next, and then last oxygen. So let's go ahead and try that. So we have 6 carbons on the left, we have 1 on the right, so if you put a 6 here, the carbons are balanced. Now let's balance hydrogens. Okay, so we have 14 on the left, and 2 on the right. And so we just put a coefficient of 7 here. That should balance the hydrogens. Okay, let's take a look at the oxygens. We have 2 on the left, And how many do we have on the right? We have 12 in CO2, and we have 7 in water. So we have 19 oxygens. So we have 19 oxygens on the right and 2 oxygens on the left. So we have a bit of a problem that I cannot think of an integer we can multiply by 2 by to get 19 oxygens. So we have an odd number of oxygens that we have to deal with on the right side. How do we deal with it? What we can do is we can write up a temporary coefficient that balances the equation. It's going to be temporary because it's going to be a fractional coefficient that we don't want to keep around too long and get rid of. So let me show you how you do that. So I need a little bit more space here, so I'm going to move oxygen over here. Okay, so recall that we have 19 oxygens on the right, 2 on the left. So what fraction can we multiply by 2 such that 2 times that fraction gives us 19? So the fraction I would use is 19 over 2. And so if you have 2 times 19 divided by 2, that's just 19. So the oxygens become balanced because there's 19 on the right. Now, as you know, you cannot have fractional coefficients in an equation. So you have to get rid of it. So the way you get rid of it is you see that it's divided by 2 here. So that tells us that division by 2 will go away if we multiply each species, each reactant and product by 2. So I'm going to take this whole equation here and multiply it by 2. And so let me get a little more space here. Okay, so we had 1 molecule of C6H14. Now we have 2 molecules of C6H14. Now we have 2 times 19 divided by 2 of oxygen. So the 2's would cancel. So now we're at 19 of oxygen. 2 times 6 carbon dioxides is 12 carbon dioxides. And then 2 times 7 waters is 14 waters. So I'm pretty sure I've done this correctly, but I would suggest to you that right now you check for each of these elements, carbon, hydrogen, and oxygen, and just confirm using these coefficients I've written up here that there is many atoms of each element on the left side of the equation as there is on the right side of the equation. So this equation should be balanced. Okay, we'll move on. Okay, so let us make a chart for this. Get a new pen here. Okay. So it looks like we may have some whole polyatomic ions that we can balance. So let's see if that is the case. So on the product side, I can clearly see that there are 2 nitrates here. So that is good. And we have a nitrate here, so it looks to me that we can probably balance whole nitrates. So that should simplify the problem quite a bit. Now, let's look on the reactant side again. And so you can see there are 2 hydroxides. And so what we might hope for is that there's going to be hydroxides on the product side. And that is not quite the case. We don't really have hydroxide. Hydroxide is 1 oxygen atom bound to 1 hydrogen atom. And instead we have water, which is 2 hydrogen atoms bound to oxygen. So we can't really balance whole hydroxides in this problem, but we can balance whole nitrates. That will probably work. So I'll put nitrate here, and then we also have calcium. And again, we can't really balance whole hydroxides, so I will balance individual oxygens and hydrogens, and hopefully that will go okay. So I want to go ahead and balance the nitrates first, so let's see what happens with that. But first, let me do a count. Sorry about that. There we go. Calcium, 1 here, 1 there. Oxygens, okay. This is oxygens outside of the nitrate, so keep that in mind. So there's 2 oxygens here, there's 1 here. And then hydrogens, let's see, what do we have? So we have 2 hydrogens here, 1 here, we have 3. And how many hydrogens do we have on the right? On the product side, looks like we have 2. Okay, so we can go ahead and try to start to balance this. So we have 2 nitrates on the right side of the equation. We have 1 nitrate on the left. So let's go ahead and just balance the nitrates by putting a coefficient of 2 here. So the nitrates are now, for the moment, balanced. Now let's check hydrogens. We have 2 hydrogens here in this molecule, 2 hydrogens in this molecule, for a total of 4 hydrogens. So we have 2 hydrogens in water. So I see maybe a way we can quickly balance the hydrogens. So I'm going to put a coefficient of 2 in front of the water. So now we have 4 hydrogens here on the product side, which should balance, it looks like the 4 hydrogens on the reactant side. So the hydrogens are balanced. So it looks like everything is balanced, but we do need to check the oxygens that are sort of outside the nitrates. Now remember, with the oxygens within the nitrates, they are balanced when we balance the nitrates. But let's look at the oxygens outside the nitrates and make sure that they're balanced. So on the reactant side, it looks like I have 2 oxygens total here. On the product side, I have 2 oxygens. So it looks like the oxygens are balanced. And so the last thing I may want to check is calcium. Calcium is balanced. So this looks like a nice balanced equation. So we're done with this. So we'll move on. Okay, so we will create a chart. Okay, reactants, products. We have sodium as Na. Looks like we have phosphorus, P. And then we also have oxygen. And then we have hydrogen. Okay, so it looks like we don't have any elements by themselves that we could balance last, so that's kind of unfortunate. Oxygens and hydrogens tend to be split up between different compounds. You see, like on the product side, we have 4 oxygens in this molecule and 1 oxygen in this molecule. So we want to probably balance oxygens either last or maybe next to last. But since we don't have a lone element, I guess it'll be last, is probably what we want to do with oxygens. So phosphoruses, we could balance maybe first, and same thing with sodiums. We may want to balance those first. Okay, so first let me just indicate how many we have of each right now to start with. Okay, so let's go ahead and just see what happens when we balance sodiums, and hopefully that will improve the situation a little bit. So we have 3 sodiums on the right. I'll put a 3 here. So we're now have sodiums are balanced. Now let's check hydrogens and see where we're at right now with that. So it looks like we have 3 hydrogens on the reactant side, and we have 2 hydrogens on the product side. Yeesh! Okay, so here, what I would try to do is think of a small number that maybe 3 and 2 can go into evenly, and then we'll maybe use that number as a way to balance the equation. So let's see. So what we want to do, we have 3 hydrogens on the left, 2 hydrogens on the right, and so what we might want to try doing is maybe putting 6 here. And then this will have to go up to 2, and 6 hydrogens. And so this will go to 3. Yeah, that's a lot of work at one fell swoop. Okay, so let's just check a few things. So we have 6 sodiums here, looks good. 6 sodiums here. We have 6 hydrogens here, and we have 6 hydrogens here. So that looks like it may have helped. Okay, so now let's look at phosphorus. Ugh. Okay, so we have 2 phosphoruses here, and we have 4 here. Oh, so we're going to have to increase this further. So let's bump this up to 4. So we have 4 phosphoruses here. Now, let's see where we're at with the sodiums. We have 12 here, we have 6 here, so I'm going to have to bump this up to 12. Oh my goodness. So 12 is for sodium. Looks like the phosphoruses and sodiums are balanced so far. Okay, let's check hydrogens. We have 12 hydrogens here, we have 6 here, so I'm going to have to bump this up further. So let's bump this up to 6. Now we have 12 hydrogens on each side. Okay, so it looks like I have the phosphoruses, the sodiums, and the hydrogens balanced. So all I need to do now is check the oxygens and hope and pray that they're balanced. So let's just check that. So how many oxygens do we have totally on the left side? We have 10 oxygens here in this molecule. We have 12 here, for a total of 22 on the left side of the equation. How about the right side of the equation? So it's 4 times 4 is 16 oxygens in this molecule, plus 6 here is 22. So yes, we were lucky. The oxygens got balanced. So it looks like this equation is a balanced equation. Thank you for listening, and we'll see you next time.